In this guided review home study problem, we have a simply supported beam. Here are the reactions: 400 pounds, 280 pounds, that are in response to a distributed load that is uniform but not over the entire length of the beam. It's only over 10 foot of the 12-foot long beam. And then we have a 280 pound concentrated force here. Right? And we're going to come up with the shear and the moment diagrams. Let's remember the critical integral relationships, that the slope of the shear diagram is given to us by the intensity of the distributed load, which also means that the change in shear is given to us by the integral of the load, or the area under the loading diagram. Likewise, we'll have something associated with the moment that goes with that the slope of the moment diagram is equal to the shear, and therefore the change in the moment is equal to the area under the shear diagram. Right? What that all amounts to is a differential equation that says the second derivative of the moment is equal to the load. So we integrate twice. That's a key kind of idea as we look at how this all plays out. Right? So we start off always in both the shear and the moment diagrams at 0. And then this concentrated force that represents the reaction immediately shoots us up by 400 pounds either side of that point, and we have a discontinuity sudden spike, so we're up to 400 pounds positive. And then we have a distributed load that is got a value of 0, so a 0 value there means a 0 slope on the shear diagram, so it comes across. So this is a 0th order or constant value right there. Then the 280 pounds then takes us down immediately. 400 minus 280 would be 120 pounds. Then we pick up a distributed load, so the slope of the shear diagram now changes. Now note, the slope of this shear diagram is going to be negative, corresponding with this downwards, or negative 40 pounds per foot, right? And for the load, and so that total change here, 40 pounds per foot times 10 feet, would be a negative 400. So 120 minus 400 would be a minus 280 pounds. And then note that concentrated load at the end will take us up, close us off to 0, where we should be. And that's not quite the end of things. We want to come back and make sure we communicate that this line that goes in this segment started off with a constant that we integrated, so it became a first order curve, straight line. And we also want to know where the 0 crossing is located. That will be important to us as well. Right? This is pretty easy to find. We have 40 pounds per foot of change. We start off at 120, so that's going to take us 3 feet to get there, over there. Right? So again, the change in shear is equal to the area under the loading diagram, and 3 feet over would then give us that 120. That would get us down to 0. Right? Then next up is the moment diagram. And note here, we start off at 0. We have no applied couple. The slope of the moment diagram, dm dx, is given to us by the value of the shear, which is at a positive 400 pound-feet per feet. Right? And so we're going to integrate a constant to get to a first order. The total change in moment given to us by the area under the shear diagram, and so that would be 400 pounds times 2 feet, so that would be 800 foot-pounds or pound-feet. And then we go and we have a sudden change in the shear, so that means we have a sudden change in the slope of the moment diagram, and so we integrate a first order curve. That becomes second, and that's basically a parabola. Now I've got it drawn as a concave down. How the heck did I know that that was going to be the case? Well, note that the change in moment is given to us by the area of the shear diagram, and that's a triangle, so that's 1/2 of 120 times 3. 1/2 of 120 is 60. 60 times 3 is 80. So sorry, 60 times 3 is 180. 180 plus the 800 would be 980 pound-feet. So that's how we know we're going up. We also, remember, dm dx equals v. So we start off with a strong positive slope that progressively gets smaller and smaller in a linear fashion until we hit zero slope. That's, of course, our maximum, local maximum, and that's what's telling me this has to be concave down. We pick up then progressively more and more negative slope, and then notice here, let's check this area then is 1/2 base times height. It is 7 foot over, so it's 1/2 of 7 times 180. And we hope that's not negative 980. Let's find out. 180 times 7 divided by 2, and it's not. Something's wrong. Let's check whether this was really correct at 3 feet. 120 divided by 40 would be 3 feet. That's good. This would be 10 foot over. We've got then 7 feet left. That remains. Oh, I know what it is, because that's supposed to be 280, not 180. Alright, 280 times 7 divided by 2. Ah, there's your minus 980. That's the delta M. From this point to that point, closes off to the 0. Again, we have a nice, smooth, continuous curve. And that little play-by-play was just to give you a sense of how do you check all these things and what should you be being aware of to make sure that you've got the right kinds of things going on.